Hello and welcome to the 7th video of my JetCar project mini-series. This video is about the firmware, the code that runs on the car itself. It is all written in Python, executed from Jupyter notebooks. Let's connect to the JetCar and log in. After a moment, it shows all the files in a notebook folder on the left side. There are 3 Jupyter notebooks, recognizable through their typical extensions. Then there's a color map CSV file from the image segmenter or StreetMaker app. There's a model weight file from the training, which cannot be opened here. And there are a number of Python files. Let's start with the lowest level, the hardware control. I used this Adafruit server controller based on the PCA 9685 chip and their server kit package. In my initial attempts, I even used RC BEC motor controllers that use servo timing. But with these I couldn't control the motors well at the lower end. So I switched to H-bridges instead. But that meant I needed full PWM outputs and not servo timing. Let's have a look at the differences. The servo signal has very specific timing requirements coming from the origin in remote control systems, where each channel gets a time slot in between the others. So the period has to accommodate all servo pulses, and each pulse gets just a small modulation around its base width for the central position. PWM signal, however, use the whole period and all possible pulse width in between. In extreme cases it can be off for a 0 signal or fully on for 100%. The PCA 9685 is actually a 16-channel PWM chip, and the servo kit from Adafruit simply restricted full PWM output to the allowed servo timing artificially. In our case, we have only one servo that requires this timing, and all other channels are better off as PWM channels. So, the servo PWM class is inherited from the servo kit class, but adds back the PWM property. This way we can choose if we want to handle any individual channel as servo channel or as PWM channel. Let's open the JetCar file as the next higher level that creates these channels. There are some comments about the steering servo and the PWM channels. In the initialization, you can see the steering channel is created as servo channel and all others as PWM channels. These 4 are used for the motors for forward and reverse. Down here are the headlights, connected to the other H-bridge board. And there are all the other LEDs. I normalized all inputs between 0 and 1 or -1 and +1, and everything outside is limited here. Depending on the polarity, some signals are inverted via 1- value. Otherwise it looks all very straightforward. However, just a last word about the differential function implementation. If the steering value crosses a threshold, then the outer motor has to get more power to push the car through the tight curve. Here's where it happens. On top are the channel definitions, and if you plug in the wires in different channels, simply reassign the channel numbers here. Let's look at the other files and classes. Here's an overview of the data flow. The camera image comes in and will be converted into a code mask via the neural network, which is then passed to the lane tracker instance, which owns lane limit objects and lane center objects. Each of these classes calls methods of subclasses, etc. After the lane tracker process call, all results can be passed to the JetCar car instance to control the hardware. Let's go to the driving notebook. Here is the call to the process method of the lane tracker instance, passing the mask and the next turn direction. Let's go right there and search for process. Here it is, and there's not much in there. It calls these three methods: get lane limits, update center classes, and process classes. There are hints in the names where they might end up. And there's the last one to handle directions. Let's search for the first one. Here it is, and there are some comments for this method. But the first actions are calling the find lane limits of the two owned instances called lane limit left and lane limits right. Let's find the declarations. These are instances of the lane limits classes for left and right. This class can be found in a JetCar lane file. And here are some comments. It contains an array of lane limit points, which have their own find limit method, and this class does also a line approximation. Here is the code for the method, and there are some comments about its task. Down here is the for loop to call the find limit method of each of its points, and further down you'll find the line approximation. Let's go back to the tracker and check the next call to update lane center classes. It first calls the get center classes of the owned instances lane left, lane center, and lane right. You can already guess that the code can be found in a JetCar center file. Obviously, the system checks the class codes in the center of its own lane and the lanes to their left and the right. At this point, I don't want to go more through the code lines, because nothing explains something better than images. So I implemented a special visualization just for this video. It's not part of the code in GitHub. In my Visual Studio Code environment, where I debug with recorded data, I added a special drawing module, and I added many calls from different for loops, etc. to get an animation of the internal flow. Here is the resulting video. It starts like the car has just received the very first code mask. You see a number of points lined up in the center, and lighter circles are coming out. These move left until they hit the lane limit on the left side. But a little bit more up, it appears the circles go out left and right, but the right ones quickly disappear. The reason is that the code doesn't know initially where to find the driving direction lane, so it checks always left and right until the first one finds the driving lane code. Then the other side is stopped and only the promising direction is followed. After that, the line approximation is performed and any outliers are moved onto the line. In addition, each point array is extended with 2 more points each on the line. This is done to limit the searches, but still get points out there. In the next step, lines show up left and right of the points, and these lines move up the point arrays. This is the lane tracker class checking for leftover outliers to correct if necessary. But this one looks very clean, so nothing else happens. After that, more points are generated, and these are in the center of the driving lane, the left lane, and the right side where there could be a lane. These points are simply middle points between the lane limits and the extrapolation beyond the lane limits. Finally, more points are interpolated in between them to create a denser sampling rate of the class codes in the lanes. More things happen in the last step. Each of the code sampling results are now compressed into run-length encoded object lists. For instance, on the left side there's a line coming from the edge up, labeled as wrong dear lane, because all the points from the edge sampled this code and have now just one list entry instead of many. This helps object tracking, and we get back to it later. Around the mask image there are also several internal field names of the lane tracker class and their contents. On top we also have a yellow triangle as steering indicator plus the numerical value and the throttle value. Let's speed it up and follow what happens. The tracked objects are always updated at the very end of each frame processing, and with the next frame coming in, there seemed to be a lag in the video, but this simply comes from the step-by-step visualization of the frames. Some specific objects are popping up on the sides with the contents of the fields. On the right side there is a next turn lane object, tracking the upcoming right turn. On the left side there's a stop yield text object, obviously tracking the upcoming stop text code ahead. It also displays the dominant arrow code on the right side, which is related to the direction arrow in the lane. Why is it called dominant arrow? Because it happens that other arrow codes show up, like the arrow left-right code displayed here on the tip of the arrow. An example of false positives. So the code tries to use some merit to detect which one is more likely. The dominant arrow should be larger in size and has a longer lifetime than the artifacts. This is the reason for tracking the objects in the displayed fields. The alive value is counted up with each frame it was detected again, and the TTL or time to live counter is counted down each time the object had not been detected in a frame. At 0, the object is removed from the list as a likely glitch. You saw how those many false objects had been removed. When reaching the stop line, the stop text is still present on the left, even though the distance is now negative. The reason is that these important text and direction arrows will still have to be kept until the intersection is passed to avoid wrong decisions. So they are moving basically under the car and they stay there as long as needed. All other objects are always deleted from the list when out of sight and the TTL is counted down. But in this case the TTL goes negative without effect. When at the stop line, the throttle is simply set to 0 and the stop counter counts down. We don't really expect anyone else to drive here, so we just continue after the countdown. With the first frame after this, the throttle is set to 1 instead of gradually increasing. This overcomes the friction of the gears and results in better movements. As a right turn was requested, the steering is now set to sharp right and another counter is started and counts down while turning. It will keep the steering to hard right, and you will see why. The class code from right turn lane has to transition to my driving direction. And a lot of chaos happens in between, where it is better just to hold the steering wheel in that position. But after a few cycles of not trying to find the lane limits, the lane tracker class starts to attempt finding them again, but now in diagonal. Another little detail on the side. So far we had seen the min-max limit checks of the lane limits always symmetrically. Here it has switched using the left lane as a base to correct the right lane points where possible. The reason is that the standard deviation of the right lane is so high that it cannot be trusted. It still holds the steering wheel right because the fixed steering count is still going. However, after 11 this counter is cleared and disappears from the display here. The lane tracker code now decided that it's time to take control again and everything goes back to normal. After straightening out, the next intersection comes to a side far away, but the right turn lane is already recognized. The next requested turn was set to left. When the car gets close enough, it initiates the left turn. And everything repeats again. Let's talk about debugging. Since it is difficult to debug directly on a real-time system, I set up an offline debug environment for the Visual Studio Code on the PC. The driving notebook allows real-time recording, which can be zipped up via executing this cell after the run and downloading. I unzipped the recording into the debug data folder of my offline debug workspace. They are all camera frames from the run, followed by NumPy files containing the code mask of the inference. And there's a log file we can open for some additional info. Now start Visual Studio Code. In the debug workspace, there are the debug files and copies of the JetCar Python files. Here's the folder name. The JetCar firmware files contain a lot of debug support, but all printing and additional drawing code is normally disabled. Here are all the control variables that can be enabled selectively. Then there is the for loop from min to max image index, reading image, mask and log file entries. There's this if image count equal statement where you can enable more debug output or set a breakpoint. Let's get it far out for now and start debugging. You can see all the debug messages for each frame scrolling in the output. After done, just copy the output and paste it in an editor, so it's easier to go through. The last line for each frame is always the contents of the log file for comparison. A good place to start looking is also the debug out folder. All debug mask images from the last run can be found here. For instance, something happened down here where the car got confused. Now you can check this image index in the recorded log file and also increase the logging for this case. You can also set a breakpoint and step through the code and see all the variables. But very often it is best to enable specific debug print variables and to check the debug outputs for clues. That's the end for this video. Thank you for watching. I hope you enjoyed it and you got interested in watching the next one. And feel free to click the like button. Goodbye.